Okay, so this might be working. Can somebody confirm that you can hear me? Is the audio working? Okay. Okay, so yeah, this seems to be working. Um, so tonight I'm gonna be working on some FPGA design. Um, More specifically, I want to design a cache for the iCE40 FPGA. So when you get a soft core like a PyCore AV or a VEX or stuff like that, and you want to access external memory, if you need to hit the memory every time that you need to read or write a word, it's gonna take a very long time, and that's just gonna kill your performance. And so the goal here is to basically use some of the memory resources that are inside the FPGA um, to as a cache, like a normal CPU cache. So first the requirements. Let me see how I'm gonna organize this. Just gonna write down some requirements about what I have in mind. I don't really pre-design or anything, so it's just gonna be basically what I'm thinking. I did previously think about designing a cache and some stuff a while ago, but I never really sat down and wrote down anything. So hopefully that will give you an insight into how I think about problems and then how I go about designing FPGA cores. Yeah. So first, requirements. So the first thing, as I mentioned, it's going to be designed for the iCE40. Specifically, wait. So this is pretty important because I don't intend it to be usable on any other FPGA really, or at least it's not going to be optimal for any other FPGA. Mostly because I plan to make use of some of the iCE40 specific things like the iCE40. Actually, the iCE40 target in particular is going to be the Ultra Plus. So basically the FPGA that you have on the Icebreaker or on the Icebreaker Bitsy. And so some of the specificities of that FPGA is the SPRAMs. You have 4 blocks that give you like a total of 128 kilobytes of onboard memory. The downside of that memory is that, well, it's single port RAM, so you only have one port, and also you can't initialize it. And so I plan to use that as a cache basically. And the other characteristic is that it's a very small FPGA, which means inevitably at some point I'll have to make some trade-offs, and I will probably choose to go with whatever results in the smallest possible logic, because I only have like 5,000 flip-flops or something. I can't waste 2,000 of them or on implementing like a super high performance cache or something like that. So the main application that I see for this cache is gonna be CircuitPython. So I'd like to run CircuitPython on the Icebreaker BitC, which is a small iCE40 Ultra Plus board, and you can connect some PSRAM, like the standard SPI PSRAM to it, the kind of stuff. I mean, you're probably familiar with it, is that this one? Yeah, this thing. Perfect. So yeah, that's a. It looks like a SPI flash, except it's RAM basically, so you can read and write to it. But it's, it's fairly slow. It's SPI, which means that you definitely need a cache if you want to use it. You can run CircuitPython on the iCE40 Ultra Plus without any external RAM. I think they do it on the FOMU, but that might be not optimal for large programs and stuff like that, and so I definitely would like to be able to use PSRAM with it. Hey, hi Zden, hi Piotr. Welcome to the stream. So that's one of the application. So that's gonna be SPI PSRAM on the BitC. The other application I have in mind is basically trying to boot Linux, probably a no-MMU version of Linux, because recently I've seen that there is a RISC-V version of a no-MMU Linux that's available, and to boot that on the Icebreaker with the quad hyper RAM mod. So if you followed a couple of the last stream from 1bit squared, Piotr assembled some of the quad hyper RAM mods, which give the Icebreaker up to 256 megabits of external RAM. So that's like 32 megabytes, which should be enough to run Linux. I mean, really, the CircuitPython one, I see as something that ends up being actually useful. Putting Linux on the iCE40 and the Icebreaker is more a tech demo than anything else, because I don't really see it as having any practical applications. But that has never stopped me from doing something. So yeah. So that's kind of the why I want this cache. So what are going to be the characteristics of this cache? So as I said, I plan to use the SP RAMs. So each of them is hey, hi George. Oh, well, I have a nice trip home. So the specs. Yeah, I'm planning on using the SP RAMs. I don't know yet if I'm gonna use all 4 blocks or only 2 of them. So it's gonna be a multiple of 2 because each SP RAM is 16-bit in width, and the PiCore V bus is 32 bits, and I want the main storage area of the cache to have the same width as the data bus. So I'm either gonna use 2 or 4 SP RAMs, which means the cache is gonna be either 64K or 128K. I'm not sure yet. It might end up being configurable or not. I'll see in the future. What are gonna be the other spec of that cache? So it's gonna be a set associative cache with 2 or 4 ways. Not sure yet how many. The cache lines are gonna be 64 or 128 bytes. So how did I choose? Those values? Okay, so the more ways you have, the less conflicts you can end up with, but the more resources it's gonna use, right? Because the cache is gonna be shared between instruction and data, and those are gonna potentially be fetching, in addresses that conflict. I definitely want at least 2 ways for the cache. No, I would tend to bump that to 4 ways if it doesn't eat up too much resources. So that's why I put it as an option. We'll see if that's a good idea or not, or if I should stick with 2 ways. More than 4 ways is definitely going to be too much resources and too much trouble for the iCE40, so I don't consider it. And I'm not going to go with 3 because power of 2s. The cache lines size. So how did why would 64 or 128 be a good number? So you don't want them to be too large, because if they're too large, when you need to fetch one from memory or write one to sorry, I was reading the Discord chat. I got distracted for a second. So yeah, if the cache lines are too large, when you have a cache miss and you need to flush a dirty cache line back to memory, or if you need to fetch one from the memory, you're gonna have an increased latency, because it's gonna take time to load those 64 bytes or 128 bytes from the actual memory. So you don't want it to be too large. You don't want it to be too small either, because the more cache line you have, the smaller the burst that you're going to make on your memory interfaces are going to be, and so your bandwidth efficiency is going to drop very sharply. And also, the more cache line you have, the more metadata you actually need to store, because for each cache line you need to store, okay, where does that cache line actually go in memory? Is that cache line valid? Is that cache line dirty? When was it last used? That kind of stuff. So I think 64, 128 would be a good value. That's something I remember from just Googling around and seeing what kind of cache line size are used in RISC-V. Also, when I think about the memory controllers, so SPI, PS RAM, and quite Hyper RAM, the burst size. So both of those interfaces, the actual memory controller is going to run at 4 transfer for every system clock cycle. So in the case of Hyper RAM, the memory controller runs at twice the frequency of the system clock and is DDR. And in the case of the SPI PS RAM, the interface to the SPI interface runs at 4 times the SPI RAM. This one is 4 bits, so that means that for every system clock cycle, I'm gonna fetch 16 bits. And this one is 8-bit wide, which means that for every system clock cycle, I'm fetching 4 bytes. So a 64-byte burst on HyperRAM that's if I have 4 byte, that's a 16 cycle burst, and on SPI that's a 32 cycle burst. And 28 bytes. Well, that's basically yeah, that's twice the value, right? So already here I can see that in the case of SPI, a burst of 64 cycles. That's pretty long. I'm not sure I want to go that large. Another reason also why you don't want to go actually above 128 bytes is because for HyperRAM, for instance, you can't actually do bursts longer than 128 bytes, so that's just a limitation of the HyperRAM. And there's a similar limitation for the SPI RAM, but I think it's shorter. That's actually something I can verify right now. Let me take a look at the chat. Yeah, definitely. Running some C application could definitely benefit from external RAM as well. Like, for instance, when I was trying to run the, what was it? The Blackmagic Pro firmware on the Icebreaker, that actually does take some RAM. Because I was trying to run everything from RAM and not even execute code from Flash. That's something that I didn't actually put here in the spec, but that I thought about, is that the cache is not only gonna be for external memory, it's also gonna be for Flash. So you basically have like a unified memory where you can fetch from external RAM or from external Flash, and it's cached independently, so you can have execute in place from the Flash as well. Because I mean, I have a SPI controller that works for the SPI PS RAM, and reading from the PS RAM is pretty much the same as reading from the Flash. Just the command number is different, basically. So that controller is gonna sit between the main memory bus of the CPU and both the external RAM controller, which is gonna be HyperRAM or SPI PS RAM, or just the SPI controller that talks to both the PS RAM and the Flash, because they're actually connected to the same pin, so it's actually the same controller talking to both. Let's check the burst size, the maximum burst size of the PS RAM actually. If there is, I remember that there's not a maximum spec of how many bytes you can fetch, but there is a maximum spec on how long you can have the chip select line low, basically. the question is, where is that specified? Okay, so you can only have the clock enables low for 8 microseconds at a time. So during 8 microseconds, let's assume a 24 megahertz system clock. The actual SPI interface would be clocked at 4 times this rate. So yeah, that's 96 megahertz. And during 8 microseconds, yeah, I can have like 768 clock cycles, and each clock cycle transfers 4 bits, which means I can have bursts of up to 384 bytes. So that's really not a limitation at all. I definitely don't want bursts that long. So yeah, the burst limitation of the PS-RAM is not an issue at all. What else? Do we have to think about? So the downstream interface. The memory controller. So the interface to the actual memory controller is doesn't have a name. It's a custom interface that I used for several of the memory controller that I designed. It's similar to iXi. Well, let me actually just draw it real quick. So it's similar to iXi in the sense that you have 3 channels. The command channel, where you send the address. You have a valid, flag. So these are inputs to the core. Then you have a ready, flag, and in addition to the address, you have the burst length and the read-write signal. Okay. So this part is pretty much iXi verbatim. That's just a standard iXi interface. So typically you set up all of the signals. So let's say that they're up, then you set them up. So that's invalid, that's invalid. You have the valid flag that rises when the command and everything is valid. And at some point the controller is going to say that he's ready. And that's when the command is accepted basically. So that's really standard iXi. Then you have the write data, the write channel. So this is used by the user to provide the actual write data to the memory controller, where you have the data, you have the mask in case you don't want to write all the words, and then you have so these are actually still very similar to iXi, But then here comes the difference with iXi. In iXi, you would have a valid signal. Here, the rule is if you submit a command to the memory controller, the right data has to be ready. You have to be ready. Like if you say that you want to write 16 words of memory, you have to have 16 words of data ready directly. You can't say, oh no, I don't have it, wait a little or anything. So there is no valid signal because as soon as you submit the command, the controller assumes that the data is going to be ready on the right channel, and it has a ACK signal so that it can say, okay, I consume this data, give me the next one. And it also has a last that tells the provider that, okay, that's the last data from this command, you can go to the next command. Technically, the last signal isn't required because both sides should know when the burst ends. I mean, if you ask for a burst of 16, the controller has to count the 16 words, but whoever submitted the 16, the command should know when the last one is. It's provided mostly because when you have some arbitration in between, what's in between might not know the exact boundary of the burst, and so it's a very easy signal to provide in the memory controller, and it's very useful for various things. So I provide it usually. And then there's a read data channel where again you have the data where the memory controller provides the data back. I mean, if you asked for reading 16 words, you're going to have 16 words of data coming on the read channel at some point. You don't know when, you don't know the delay or anything like that. That's why it provides a valid, or actually it's more like a strobe. Because again, in a normal iXi bus, you would have a ready signal so that the client to the memory controller basically doesn't have to be ready all the time. Here, that's not the case. If you ask for, okay, you ask the memory controller, read me 32 words, you have to be ready to consume 32 words like directly. Like, if you're not, well, that's your fault. So that's why there is only a data and a valid, and there is no ready or anything like that. So yeah, that's pretty much the way the memory controller interface works. Is there a chance of getting some kind of error? Well, last does not match. Well, yeah, that's why. Like in iXi, for example, for the right channel. Oh, sorry, I forgot. In the read channel, you also have a last. I forgot to say this. In iXi, the last is actually in the other direction. But then you can have a case where you tell the memory controller to write 16 words, and then you only provide 15, and you assert last on the 15 one, and then you have some kind of mismatch. And okay, what do you do? And that implies that your controller must have some error recovery logic and all that stuff, which is just annoying because it costs logic. And for me, it's a waste of logic. That's why here the memory controller provides you the last and tells you, okay, that's the last word I'm gonna take. Well, if you have more to provide me, well, don't give them to me, I don't care. And if whoever sends the command doesn't, sends the right amount of data, well, it's not the controller's problem. That's kind of, exactly. Don't make mistakes. The thing is, like handling all the possible error case and mismatch and all that kind of stuff, that tends to cost a lot of logic. And since most of the time I tend to try to have very small cores, I don't want logic to deal with errors that shouldn't happen in the first place. Like if your design is written properly, you should be able to prove that this can't happen. I mean, except random bit flips from cosmic radiation and stuff like that. But I'm not designing a satellite that has to, operate or that kind of stuff. So I don't really care about those kind of errors. So yeah, usually I try to go for just do things properly and don't deal with errors. Okay, so yeah, that's the memory controller interface. Now the interface to the let me go back to this. So I would call this the downstream. So the upstream interface, or the main target. So Esden is asking about the cache implementation in Lytix. I didn't like the. Well, let me first grab something to drink, because as it turns out, talking all the time. So there are already possibly several caches in Lytix. One of them is just built into the VEX. Like the VEX has a cache feature. You can build the VEX RISC-V CPU with built-in instruction data cache. I would actually make use of this, at least the instruction cache. The downside of these caches is that they are write-through cache, which means basically they only read cache. When you issue a write, it goes and hit the memory directly. That's the that's the way the cache works in the VEX itself. Now, Lytix also has. Honestly, I have no idea if it's write through or write back. But the way I've seen it implemented was a little weird, in the sense that, okay, if I understood, let me go back to this. So my understanding of the Lytix cache architecture is that you have the memory controller, then you have the cache, which at that point is pretty standard, and then here you have the CPU. Okay, so obviously nothing wrong with that, right? But here, this interface, as far as I can tell, that's wishbone and just very wide. So if somebody can correct me, maybe I misunderstood it, but basically if they want like a 32-byte cache line, well, this bus is gonna be 32 by 8 bits, basically. So how much is that? That would be 256 bits, right? So that's a 256-bit wide wishbone bus inside your FPGA, which on an iCE40 doesn't sound like a great idea. Yeah, that is massive. And so if somebody who's familiar with the memory architecture of Lytix can correct me, maybe I misunderstood, but that's the way basically that I saw that they were, because the memory controller, like in DDR and stuff like that, they really want to burst, right? You don't fetch just one word basically, and the way they implemented bursts over wishbone, which is basically by making the bus very wide. Yes, exactly. The cache is gonna talk to the memory controller. So basically, the only difference is that here, that would be my memory interface, which I explained in here before, which is much more similar to AXI than Wishbone, and it's optimized to basically try to save as much logic as possible. And that's already the interface. Like if you look at the, yeah, obviously you're the only one who can look at it, but the HyperRAM controller that I wrote already uses that kind of interface. It's pretty easy to use. It's and instead of transmitting, because if you do a very wide wishbone, you're basically transmitting your entire burst at once, basically, right? While here you transmit it in several clock cycles, but you don't really win any speed with the very wide wishbone, because well, you still have to wait until the very last data arrives anyway, so yeah. Let me catch up on the chat. Yeah. Okay. What else did I need to say? Yeah, and something else that would probably be in at least some of the SOC that I design would be something like this. Let me. It's basically have an arbiter between the memory and the cache, and have a DMA engine at that point, which can do things like driver display, for instance, like the HDMI P mode or that kind of stuff. DMA is controlled obviously by the CPU, but it doesn't go through the cache, and it can access the memory controller interface directly. And if that arbiter had to operate on a 256-bit wide bus, I mean, just a simple mux would literally take 256 slots, which is like what? Is that like 5% of the FPGA in a single? It's like 5% of the FPGA for one mux. That's yeah, not a good idea. Thinking about, because I'm planning to use the same interface on the ECP5 as well. So this memory controller is targeted at the iCE40, right? That will definitely be writing a cache as well for the ECP5, where some of the choice are gonna be different. And one of the things that I want to implement, for instance, is if you're asking, you're trying to access a memory which is not currently cached. So let's say this is your cache line, and you want to access this word inside it. if it's not already loaded, what's gonna happen usually is that the memory controller is gonna read the entire cache line like this, and when it's at the end, it's gonna say, okay, you can read the value, right? But something you can actually do if you want to reduce the latency of your memory access for cache miss is most of the IPRAM, for instance, supports wrapped burst mode, where the memory controller will actually start the burst here and then go for 64 or 128 bytes, and the IPRAM itself will actually wrap and continue the burst here. And so what you can do is you actually populate your cache during this entire period, but you can already return the correct value to whoever asked for it at this point. And so you've reduced the latency of your memory access in case of cache miss, which is something you can't do at all in Lytix and that kind of stuff. But yeah, that's for a more advanced cache controller. This is not what we're going to be working on today. So let's go back to the requirements. So the upstream interface. I've got two CPUs that I want to be able to talk to, the VEX and the Pico LV32. Now, both of them can offer a wishbone interface, and that's definitely going to be the main target. With potentially some optimization, in the sense that, as I said, the VEX RISC-V increase the font size. Oh wow, that's a good question. How do I do that? Does that work? Is that large enough? So the VEX RISC-V can include an instruction cache, and even if I have a large shared cache between instruction and data, I might still want to include a small instruction cache inside the VEX, because it basically serves as a fetch buffer, so it doesn't even have to go outside of the core itself to get the next instruction, and that allows to speed things up even more, because when you're talking, I mean, if you look at a simulation of the VEX or the Pico LV, like the VEX literally spends like 1 out of 2 or 3 cycles waiting on memory, so you're like literally wasting 33% of your performance just waiting on memory, and that's when your program is executing out of block RAM. So like that's the fastest memory you can get in the FPGA. The Pico LV is a little slower. I mean, it's slower in terms of cycles because it only spends 1 out of 4 or 5 cycles waiting on memory. But still, that's pretty significant, and you definitely want to be able to keep them fed with instruction, else you have logic sitting there doing nothing. And the VEX RISC-V, although it has a wishbone interface, you can also have a native burst interface for the instruction bus. So the VEX35 has two bus, one for the instruction and one for the data. And if you implement the instruction cache, instead of doing individual access, you can actually ask the VEX to just only do burst access. And so you could read an entire cache line from your level 2 cache into the instruction cache instead of doing it word by word, and that would be obviously much faster. And some specialization that we might do for the Pico RV32 is that the Pico RV has, let me see how that's phrased. Do I have a Pico RV32 somewhere? Well, I can actually, I'm just gonna go on GitHub. So if we look at the source, wait, let me cruise the font size zone here. Pico RV32. So yeah, we have this thing. So the Pico RV has this kind of look-ahead interface where it basically gives you the address one cycle early. So it kind of allows you to see the future. The downside of that interface is that that's a combinatorial output. That's not the output of a register, which means you've got a very long combinatorial path in front of it, which means you really can't do much computation on it without killing your timings, basically. So that's kind of the downside of it. I don't know if we can see exactly what is... yeah, I mean, we already have like a mux here. It's not actually that bad. I mean, I'm assuming that's a register. I'm assuming next PC. What is next PC? So next PC is another mux. So yeah, it's like two mux, one after the other. So yeah, it's not great, but it's not terrible either, which means that that might actually be useful. But so yeah, the Pico RV has this look-ahead interface, which we might be able to specialize for. So yeah, in the upstream interface, basically we're gonna default to Wishbone. We have to be able to support just plain old Wishbone, but we might add some optional specialization for the Pico RV32 or the VEX to allow higher performance when possible, basically. So I think that's basically the requirements. So now we need to sort of, because, yeah, to make some choices, basically. So, wait, can I have... Let me see if I can do this. Okay, no, I'm just gonna switch to this. So, oh yeah, thank you, Piotr. We need to make some of those choices. Let's see what kind of stuff they imply. I would like to display... I don't think I need to display the. Okay, well, I'm just gonna write them down. So we have the total size of the cache, 64K, 128K. We have the number of ways, 2 or 4. We have the cache lines, which are going to be 64 or 128 bytes. Oh yeah, there's something else I didn't talk about is the address space. Like how much memory total can we support? So this is reasonably, we're not gonna have more than 256 megabits of dynamic RAM because that's the quad P mod. So you just can't make more of that. And then we have the flash as well, so let's just double that. So that'd be 512 megabits address space basically, which is 64 megabytes. So the total address space would be at least 64 megabytes addressable, which would typically be probably like 32 megabyte of RAM and oh wait, I just noticed my laptop isn't plugged in. I need to find power first. Yeah, okay, sorry about that. So yes, I say the total addressable space, 64 megabytes, 32 megabytes of RAM, and well, 32 megabyte of flash, but I think on the both on the icebreaker and on the BitC, it's only 128 megabits, which is 16 megabyte. But yeah. So that's our 32-bit address. How is it split? Well, we have 2 bits, which are just 0, 0, because we really only deal with 32 bit words and not actually bytes. Then we have the offsets, which is the offset of the word inside of the cache line, which the number of bits depends on the cache line size. So in this case it would be for 64 bytes we have a 4-bit offset, and we have a 5-bit offset in the case of 128 bits. It's correct, right? 64 byte is 16 words, so 4 bits, yeah. After the offset, we have the index of the cache line, and then we have the tag, and then we have a part that's not actually used. So the part that's not actually used, if we have 64 megabytes, to address 64 megabytes we need let me do some math here. Well, let me type some math on the computer. So we need 26 bits, which means we have 6 bits which are not used. So yeah, that's 30 bits, and that is 26 bits. So here, what I'm trying to do is try to see the impact of these the various decisions that I make. Oh, nice! I can actually see my cursor. Perfect. Yeah, see the impact of the decision that I make on the design, and see if I hit something that I don't like or something like that. So. As I mentioned before, the cache line size, 128 byte, that seems very large, because that's gonna be a 64 cycle latency to fetch data from the SPI PS RAM. That seems very long to me. But let's keep it for now. So, okay. I need to compute the size of those various fields for the various possibilities that we have here. How am I going to do this? Because there's going to be a lot of values. Okay, well, I'm just going to so we have 1, 2, 3, okay. That's gonna be the cache size, that's gonna be the number of ways. That's gonna be the cache line. So let's start with 64K. 2 ways, 64, 128. 4 ways, 64, 128. And then we have 128K. So these are all the possibilities that we have, and we'll see exactly what they imply. So something I haven't talked about yet. As I said, the main memory area where we store the actual cache data is going to be the pseudostatic, the SP RAM, sorry, not the pseudostatic, the single port RAM in the iCE40. Now, for every cache line, we also need to store some metadata, and those are going to be stored in block RAMs. So for every way of the cache, okay, maybe actually maybe I should explain. Okay, I'm just thinking maybe not everybody knows how set associative cache works, so maybe I should actually cover that very quickly. What the fuck did I do? Okay, first just trying to see if there is a good explanation of all cache works that I could just show. Okay, so that's really pretty good. That looks. Let me zoom in this. So that's our set associative cache works. Is that you have the entire memory zone covered by your cache, which is relatively small compared to your main memory, like 32K or something like that. Then you overlap it several times over your main memory, and it's divided into different cache lines. And for each cache line of your cache, it can be mapped to the main memory zone it overlaps. So you see cache line 0 here, it can contains block 0 of memory, or block 64, or block 128, or block 192, stuff like that. So every multiple of 64 in this particular example. So cache line 0, for instance, can never contain data from block 1. It's always aligned to kind of its position, if you will. And then this example is actually a one-way cache. When you have several ways, like 2-way, 4-way, stuff like that, you basically have this repeated several times. Wait, what is this? Oh yeah, okay. So wait, okay, they call the way set here, so that okay, that's a little weird. But the general idea is that, yeah, I'm not sure I'm actually the best at explaining. Yeah. As you say, Piotr, the image is for a two-way cache. But then what's actually weird is that here they say this can point to block 0 and then to block 64, but this should also be able to point to block 32 in this case, because if both cache line 0 and cache line 1 are, I mean, if you only have 31 sets, 32 sets, that means that cache line 0 can map to block 0, block 32, block 64, all the multiples of your number of sets, basically. So that's why this diagram, I think, is not perfect. But you can see here that you have your memory zone is divided into the offset inside the block, the index, which is the set number, basically, and then the tag. The tag is basically the MSB of the address, and that part you need to store. Basically, for each cache line, you need to store some metadata, which is the tag, which is, okay, the data I have in my cache at that particular cache line, I need to store the MSB of the address that it corresponds to, because that's something I don't know. Like the LSB of the address, they're implicit, because they're composed of the offset inside of the cache line and the index of the cache line that gives you the LSB of the address. But the MSB you need to store to say, okay, cache line 0, it actually comes from block 64. And you need to know, okay, in set 0, way 0, this cache line corresponds to this particular address in main memory to know if it's a cache hit or a cache miss. Yeah, exactly. So for every entry in your cache, you take the tag, which is stored in metadata, the index, which cache line you're actually accessing at this very moment. So like if you're accessing cache set 31, tag plus set 31 plus the index inside the actual cache line is going to give you which very specific memory location this cache entry corresponds to, basically. So when you yeah, that's the general idea. So let's go back to this. And so yeah, I have pretty much the same notation as they have. And so to store those metadata, so okay, what metadata do we actually need to store? So for every cache line, we need to store the tag. We also need to store other data. We need to store at least 2 bits. One that indicates if this cache line is dirty, is valid. So okay, in that particular cache line, do I actually have data at all? That means something, because at boot the cache is empty, so you can't use it, obviously. And dirty is okay. Has that cache line been modified since it was loaded from memory? Because we are designing write back cache, that means that every write that the CPU does to memory only modifies the cache, right? It does not actually hit memory directly. It will hit memory at some later point when we decide to flush the cache, basically. So we only need, at least need those 2 bits, and we're probably gonna need 2 other bits that mark the age of this cache line. Because, okay, imagine that your cache is full, then you try to access a memory zone that you've never accessed before. Well, you need to load that data into your cache. Okay, but your cache is full, which means that you need to evict something from the cache. And one common algorithm to use is basically the LRU, least recently used cache line. And so you basically evict, whatever data has been least recently accessed. But to know which data has been least recently used, you actually need to store when is the last time you used it. And because we have 4 ways, we can choose which of the 4 ways we evict. And I mean, we have 2 or 4 ways. We can choose one of those ways to evict, and so we need 2 bits to store the age, or 1 bit if we only have 2 ways, basically. So Matthew posted a link to the link that Matthew posted looks exactly like this, including the metadata. It's missing the dirty bits. So I have no idea how to pull it out, because I have the Twitch chat on my laptop and the streaming on a completely different machine. But you can follow the link. Yeah. Oh yeah, and as Matthew said, in the Hackaday badge, there is exactly that kind of cache implemented. It's a two-way cache set associated as well. Exactly the same kind of design that we're doing here, basically. But it was targeted at the ECP5, and it's also not super readable. So that's the metadata we need to store in block RAMs, and the block RAMs in the iCE40, well, they have several modes, but the only one that's gonna be really useful is 16-bit data bus, and I think it's 256, so that's an 8-bit address basically. So that's what we can store in one block RAMs. Okay, so let's compute the size of the various fields in those various cases. So offsets, the number of bits in the offsets, so that's 4, 5, 4, 5, 5, 4, 5, okay. The size of the index, so that's gonna depend on the number of ways and on the size of the cache. So I'm just gonna, so obviously if we have a 64 K cache size and we have 2 ways, that means that each way is gonna be 32K, right? If we have 4 ways, well, each way is gonna be 16K. So this is gonna be 32K. 32K, 16K, 16K, 64K, 64K, and 32K, 32K. So 32K is 15 bits. That's 14 bits. 16 bits. And that's 15 bits. So the way size is essentially this. Like this part from here to the end. That's the way size. So if we want to know the size of the index, well, we take the number of bits in the offsets, or we take the number of bits in the way size, we subtract 4 or 5 and then 2, and that gives us the size of that field basically. And so in this case this would be 9, 8, 8, 7, 10, wait, 11, 9. Just basic arithmetic sometimes it's just hard. 9 and 8. Did I screw up anywhere? I think that's correct. And so then we have the number of bits in the tag. which is basically, if we want to support an address space of 64 megabytes, that's 26 minus the way size. So 11, 12, 10, 11. Okay. Let me recheck something here. I want to recheck the size of the iCE40 block RAMs to make sure that I didn't screw up. So yeah, that's when they're in 16-bit mode, they are 256 entries. So when looking at some of these options, now wait, let me go back to this. Like there's like 10 bits of index. That means that for each ways I have to store 1024 entries, which means I need 4 block RAMs per way. That means I would need 16 block RAMs just to store the metadata. Yeah, that's way too much. That's not gonna happen. Honestly, I don't see myself using more. I mean, no, I only have 2 ways. So let's actually number of the number of block RAMs that I need to store the metadata. So that's gonna be the number of ways multiplied by 2 exponents the number of tag bits minus 8. Yeah, no, I just need to do the math, right? No, wait, I'm wrong. Number of ways multiplied by 2 exponent the number of index bits minus 8. So this would be one, no, 2, so one way would take 2 blocks, and there's 2 ways. One way would take 1 block, there's 2 ways. Four, sorry for all the arithmetic, but I need to see exactly how things are gonna fit. What time is it? Oh wow, it's took a long time. So 10, oh man, 10 bits. That means 4, say 8. That's just insane. 4, 8. and 4. Okay. So that's a pretty important column because this is going to drive a lot of the choices. I definitely don't want 8. No freaking way. I'm wasting 8 block RAM just to store metadata. So that's not happening. Now the question is, do I want which means if I want 128K of cache and 4 ways, I need to have 128 byte cache lines. Huh. Not, as I said, I'm not a super big fan of 128 byte cache lines. That seems huge. But on the other hand, I'm not, I don't know if I want to use all the single port RAM for the cache or not. So one thing I'm thinking is some of the code I basically wanted to execute from fast RAM all the time. Like yeah, so parameterization as limits. And I would definitely, every time I have the opportunity to make it, I do. But the cache size is definitely going to be only 128 and or 64K. The reason is you need 2 SPRAM blocks to form 32 bits, and there is 4 of them, so you can either use 2 or 4. And I will only use SPRAMs for the data contents because that's well, that's where you have the most amount of storage, basically. So that's the thing. Now, the number of ways that's a lot harder to make configurable. Because we'll come to it later. But some of the things I see, it'd be harder to make configurable. The size of the cache line, that should be easier to configure. So. So we might be able just to switch between, if we attribute all the SPRAM to 128K, is to use 128 byte cache lines. Yeah, it shouldn't be too hard to make it configurable and possibly use 8 EBRs. But at the moment, the configuration, at least I would target as the kind of the base one, the one that must work if we don't configure anything, would probably be this one. I think that would be my main target. If we can make something configurable, we make it configurable. But if at some point it's just too hard, that might be the golden one. So the reason I'm not using all the single port RAM is because, well, it'd be nice if the user could make use of some of it for other stuff. Basically, that's kind of the main reason. And I think 64K of cache is already pretty significant for the kind of program that's gonna run on it. And if you really want to bump it to 128K, yeah, you can. Some other potential use for the other PS RAM is to basically just have block RAM, have code in block RAM all the time. And that's not an external RAM. Like I'm thinking, you know, if you want circuit Python running on the BitC, you basically have a USB stack that needs to be running all the time, and you want that to be very fast. And so running it from dedicated block RAM might actually make more sense than relying on the cache. The other option is see if when we write the cache, if it's possible to actually lock some of the ways, so you can actually dynamically select, okay, I'm loading this part of code, and okay, load it in cache and lock it so that it's never evicted. That's another option if you want code that always runs fast, basically. Things like interrupt handler or yeah, the USB handler, that kind of stuff. And so in this configuration, that means that our tag, we would have 12 tag bits. And so here this would be 12, and which means the total is 16 bits. Oh, convenient. It's always nice when things, you know, fit perfectly into the kind of resources you have. Okay, so we have an idea of the size of the various fields and how things are gonna work. So we can start working on how is the core gonna look like. So I think I'm gonna just design, work on the fast path. So what I call the fast path is basically the cache hit. Okay, if your cache is you know, working well, you should get a lot of cache hits. That's kind of the goal of the cache, right? Which means that's the case that you want to optimize for. That should be the minimum amount of latency that you can possibly do. Sorry, catching up on the chat. Core bound RAM. I have no idea if it's the correct term or not, honestly. So then I'm gonna say, at the very least, we'll need a few kilobytes at least of not even SPRAM, but just block RAMs, because we need to boot the core from something. So on the Academy badge, Sprite did something pretty smart, is that the cache is initialized with the boot code, basically, which is very convenient. Unfortunately, we can't do that here, because we store all the data inside SPRAM, single port RAM, and in the iCE40, the single port RAM, you can't initialize it. The SPI controller is also not usable on boot because it's gonna run pretty fast. It's gonna run at 96 megahertz. This is actually gonna require some read training and memory training as well, which means you can't boot from it either. Which means you inevitably will have to add a tiny bit of block RAM that you initialize. That's gonna be your bootloader. At least on the iCE40. For the Vextrix 5, something I was thinking of is, because I would most likely add a small instruction cache inside the Vex itself, This could actually be used as the boot memory. The VEX doesn't support that at the moment, but asking around in the Discord chat of the VEX, oh wait, no, not Discord, the Gitter chat of the VEX, they kind of showed me where I would need to patch that in, and so that might be an option. But for the PyCore RV, we'll need small programs somewhere else to boot from, whose job it's gonna be to basically initialize the SPI flash and SPI memory controller, do all the read training, switch them to runtime mode, and jump to the main code, copy it from flash to RAM, or just jump to flash directly, that kind of stuff. So, how is this thing gonna work? Let me actually, give me a second to grab something to drink first. Sorry about that. So, SD composite core coupled memory. Okay, yeah. It's pretty common to have like a small piece of SRAM. That's always accessible no matter what. So we have 4 ways. Okay, so we have the address. So what's gonna happen most of the time is reading memory, right? Just because instruction fetches and data read are just more common than writes, but the data writes are not gonna be all that different. So we have the address coming in. Okay, that's a good start. No, we need to know if we have this if it's a hit or miss, basically, which means we're gonna need to look up in every tag memory, if we have this loaded in the cache or not. So we do a parallel lookup in all 4 of this memory. We also need to keep that address for the next stage, so we need to register. So we're gonna need something like this. Okay, that's the first step. Okay, so what we're doing here is basically we're using the LSB of the address. So remember, I'm just gonna rewrite the structure of the address on the top corner here. So we have the tag, the index, the offsets, and then we have 0. Okay. Yeah. So what we do in this first part is we take just the index part of the address and we use that to index and fetch inside the tag memory which tag is currently stored. So and if it's valid or not. Um, and so this is for way 0. This is for way 1, this is for way 2, this is for way 3. Okay, so we retrieve the tag. Well, we need to check if it's actually a match or not, right? So we need something like so for every way we check if the tag that's actually stored for that way is the tag we're looking for or not. And additionally, if it's valid or not, because if hey, hi, welcome to the stream. Feel sorry for you. Okay, so here that's a valid signal that indicates if it's a match and if it's valid. Next, we actually, assuming that there is a match, okay, because we're concerning ourselves with only the fast pass, so we're just assuming it's a cache hit at the moment. We need to select which way to access. So I'm going to draw that. Yes. Sorry for the silence. I'm just drawing and trying to explain. So, okay. We looked up all the tag. We assume we have a match, and here we at the end what we want is okay. Wait. What did I do? No, that's actually completely wrong. Because we don't care about the tag. The tag, we have it from the address. Why did I do that? Yeah, no, that is completely wrong. What we care about is which way we need to access. All we're interested in is which way contains so catching up on the chat. What we need to know is which way is it contains the valid data basically. If it's 0, 1, 2, or 3, and yeah. So do we care about some other data? Not really. Wait, let me redraw that because that's actually more complicated than it needs to be. Well, I'm not sure why I thought we needed to mux between the various outputs. We definitely do not. Yeah. So from the various match, we need some logic that's basically just gonna generate the way number, which is basically 0, 1, 2, or 3. Okay. Then we actually need to access the data itself, right? So we have our giant so that's the SPRAM. And so if we have the way number, so the address inside the SPRAM is essentially composed of the way number, the index, and the offset. The index and the offsets, they come directly from the request. And the way number, well, it comes from our lookup in the tag memory. Check tag and valid. So wait, just catching up on chats. Oh, thank you. Yeah, yeah. I mean, I always design with diagrams. That's just the way I design stuff. An recommendation for a simulator I could use on both Windows and Mac. Well, either Verilog or Verilator should both work. On Windows and Mac. Yeah, especially nowadays with Windows system for Linux, WSL, you can pretty much run anything. But I don't know if the toolchain from Xobs has actually anything packaged. Uh, One thing you're gonna need as well is waveform viewer, because both the simulator just output a VCD file or a LXT file or anything, and so you're gonna need like GTK wave or something to actually view the waveforms, unless you enjoy reading VCD by hand. But that's personally, I use iVerilog more than Verilator because it's closer to kind of a classic simulator. Verilator is a little bit different. In the sense that you need to write a C++ test bench and switch clock cycles yourself, and it's also a bit easier to shoot yourself in the foot. And also it doesn't support some things that I use commonly, like in-out ports are not supported, and so when you're trying to simulate some of the vendor I/O blocks and that kind of stuff, that's just not supported. So you have to work around it. It's a bit annoying, but it's also massively faster. But the truth is, for like small things like that I run in ECP5 or in the iCE40, the designs are so small that iVerilog is perfectly suitable for that without any issues. Okay, so I think that's actually our fast path. So here we'll have the data, and obviously we will have some logic here that generates or acknowledge. You know, if we have a hit, we generate an acknowledge. If not, notes. Something else we need is we will need to update the age. Because if we implemented like a least recently used cache eviction policy, that means every time we access a cache line, we need to update it as being the most recently well used one. And so we'll have the right side of the various memory, where we're gonna need to write the new values basically, and so this is where okay, yeah, that's so what we're gonna need to update is the age field, and in case this happened to be a write and not a read, we also need to update the dirty flag. And so that's where we're actually gonna need the values. Okay, so this got a little messy in the end, but that's the general flow. So as you can see, that means that for every address we get, it takes us 1-2 cycles before we can actually provide data to the CPU. Now, if we only had like standard SPRAM, like a small SOC-do, you know, if you look at the PicoSoc demo example or something, you just have a SPRAM. The data is provided in 1 clock cycle, which means that we have 1 extra clock cycle of latency. This is going to impact the performance of our CPU. Most likely in the case of Pico V32. So Pico V32 takes, you know, about 4 cycles to execute an instruction. It's, you know, it depends on the instruction, that kind of stuff, but usually like 4 cycles, including 1 being the memory fetch latency. Well, now it's gonna take 5, which means that you've just lost like nearly 20% of performance. Just because of the cache. The VEX, it's a little harder to compute because, as I said, I would actually instantiate it with a built-in instruction cache. And so the impact of 1 additional cycle of latency is not very clear, especially since that's a pipeline, right? Which means you can actually feed the next address before you wait for the end of this one. And as I said, in the case of the Pico RV, we could actually, because of the lookup interface that's available, we can actually have the address 1 cycle before. And so we could actually hide the latency of this step, right? You can, something you could do is that instead of the address here, you provide the lookup address, and instead of the address here, you provide the real bus address, right? And this way you kind of win 1 cycle in the Pico V32. The question, of course, is, okay, will it meet timing or not? Well, that will need to be answered. But then, in the first case, we're just designing for standard wishbone, and that's not applicable. So that was a read. For a write, there is really no difference because you would just have the data on the top, and the data would actually just come here and just feed into the data right of the SPRAM. The address is the same. The only difference is that the write enable is going to be gated with an end. Okay, is it a hit or not? If it's a hit, we can write it. If it's not a hit, well, we must definitely not write it, because else we would just corrupt the cache with indirect data. So of course that's the fast path, which I think should not be too big. I mean, if we took a look, okay, so check, tag, and valid. Okay, those small blocks here. Really, all they are comparators. They compare the tag value, which we said is 12 bits, and they compare the value that's retrieved from here to the hit, and we also need to check the end flag. And so, like, once you it's a LUT4 architecture, which means if we want to compare 12 bits, we need 6 LUT4. So that would be that's a 12-bit comparators, right? You have the 12-bit reference value that you input here, and one output, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 LUT4 and 3 layers of logic. And potentially this one might be mergeable with the previous layer of logic or not. Because really the only output that we need is it a hit? Which is the OR of the 4 signals. And we need the way number. Which is 0, 1, 2, or 3. So, I mean, I don't have the exact logic in my head, but I don't think that's gonna take more than two additional layers of logic, right? Which means we'd be at 5 layers of logic. My target frequency would be around 30 megahertz. And 5-layer logic in the iCE40 at 30 megahertz, that would work. There shouldn't be any issue with that. We can quickly check if you want to see how you check for that. So here I'm thinking about, okay, am I gonna meet my target frequency basically? I have a read from a block RAM, and then I have 5 layers of logic, and then I have a lookup in the SPRAM. Let's say 6 layers of logic. Let's be like pessimistic. So we have 6 layers of logic, which means we have 7 interconnects. Oh wait, I just noticed I'm not drawing on the right screen. We have 7 interconnects. We have the EBR clock to out. We have 6 LUT4 delays, and we have the SPRAM setup time. Okay, so let's just look that up. Okay, yes. I'm actually gonna use this window. Open FPGA, share, icebox, timings, okay. So the block RAM. So these are the timing for block RAMs. We have a clock to out, setup time, IO path. So worst case scenario, from the clock to the data out, we have 1.3 nanoseconds. We have the LUT4 delays. So the LUT4 that's implemented in logic cell. The delays. So from the slowest input to output is in 0 to LC out. And so the worst case scenario is 1.3 nanoseconds. So we have 6 times 1.3 nanoseconds of delay. Then we have the setup time of the SPRAM. SPRAM setup time from positive edge of the address. So the address setup time is actually very short. 260. Are the control signal worse? So the mask is even shorter. Write enable is 288. Yeah, it's like 0.3 nanoseconds, so that's really fast. So these are the delays. The interconnect, unfortunately, that's not. I'm just gonna see if the number seems reasonable, but basically, if you multiply your delay by the logic delay by 2, and it fits within a timing budget, that should be fine. So here we have. Let me do the addition. 6 multiplied by 1.3 plus 1.2 plus 0.3. Except I didn't write that correctly. So that's 9.3 nanoseconds of logic delay. If I'm targeting 30 megahertz, that means I have a 33 nanosecond budget. I have a 9.3 nanosecond logic, which means I nearly have 20 nanoseconds of routing delay. That's like twice my logic delay. Okay, that's gonna fit the frequency, like no problem. That's not gonna be in the critical path at all. So that's good, because that means that the fast path of the cache is not gonna influence the frequency of my sock, and it has ample margins, which means that the placer should be able to have some flexibility to place it around the chip to better place other components that are more critical. Now, of course, that doesn't mean that other part of the cache won't have any critical path. They might very well, but the things like the state machine that's gonna go fetch the cache line, that kind of stuff. Fetching the data is gonna take like 32 cycles of just fetching the data from the actual PSRAM, the SPI external RAM. If it takes 32 cycles, that means that if at some point I need to register something to add 1 delay of latency in a state machine somewhere, I go from 32 to 33 cycle. It's really not the end of the world, right? It's not gonna affect the performance that much, because first it's only 1 more cycle over 32 cycles, and that only happens in case of cache miss, so that's not a problem. If I had to add a pipelining level somewhere here, well, that would influence the performance of my sock a whole lot. And so the fact that this won't be anywhere near the critical path is good, and the data output to the sock is directly the output of a SPRAM. I mean, obviously, the cache is going to integrate within the larger stock, which means here you will actually have a mux with the peripheral and possibly some what do you call it, like a core coupled memory, something like that. But that's like 1 mux, and you have it anyway. It's not part of your cache. And the input of the address, well, you have like a register here, and then you have the EBR memory. And if we take a look at the timing of the memories again, do I have that somewhere? So the setup time on the read address is 0.4 nanoseconds, which means it's really short as well. Which means, like, the address here, even if it's combinatorial, the fact that it goes to a block RAM, you only need a 0.4 nanosecond setup time, which means it doesn't eat a whole lot of your timing budget, which means we might actually be able to use like the Pico RV look ahead interface for it, because we only use the address to do the lookups in there and to go to a register. So we don't do any complex like logic on it. So yeah, that should go over pretty well. So the way I see the general cache working is that it's gonna have 2 operating modes. Is that by default it's in I don't know how I'm gonna call it, like runtime mode, where it basically executes only cache hits, right? And if at some point a miss is detected, well, this signal is going to be low, which means we won't acknowledge the bus, which means the bus will actually constantly resubmit the same request without being hacked. And an internal state machine is basically going to switch over to another operating mode, where, so you have the runtime mode, where it's only cache hits. And if we have a miss, we flush, so this miss dirty, and then miss clean, load, okay. So that's basically the 3 kind of major modes that the cache state machine is going to have. Is that runtime, it basically executes whatever is incoming on the bus, and if it's a hit, it acts to the bus. If it's not in runtime mode, then it completely ignores any requests from the bus at all, basically, and doesn't acknowledge them, which means that the bus will just stay there with the request active, and not being active, so the bus is basically waiting. And instead, okay, if we need to know the new cache line somewhere, but the current cache line is dirty, which means that we have some data that we wrote to the cache that hasn't been written to the external RAM, well, first we actually need to write the entire cache line back to memory. Once that's done, then we can load the new cache line from memory to the main SPRAM. And once that's done, we can just go back to runtime mode, And in runtime mode, the bus access will still be waiting. We'll start executing it. At that point, it will be a hit because we literally just loaded the correct cache line, and it will continue. So that's the basic operating principle. So obviously, this diagram here is obviously incomplete because that's only the runtime path, right? Which means in front of, because it's a single port RAM, in front of the address and in front of the data and in front of the write enable, we'll actually need a MUX, an additional MUX, so that we can either access the SPRAM mode for bus accesses or for memory accesses when we load or flush it. Same thing for the right side of the tag memory. We need to be able to update it with the new infos. Yeah, and I think that's basically it. So we just have one more mux in front of here and in front of here. We won't actually need to fetch any other information from these because we only perform load and flush if the bus requested something. So yeah, I think we're good there. Did any of this make any sense? Does anybody have any question? Because I think I'm gonna stop here as far as the design go and design the actual like logic for the flush and the load on another stream. But if anybody has any questions, or I wasn't clear, or I have no idea if you have been able to follow at all my train of thought, because I didn't design this before, so that's literally all I'm thinking, and I'm just thinking out loud, and I can imagine it's not necessarily easily to follow. Well, thank you, Matt. Okay, then I think I'm just gonna end things if nobody has any questions. Okay, well, thank you for great. Well, thank you guys for joining, and okay, yeah. I hope I will do this again for the rest of the design and actually get to the actually writing code and debugging it. I have no idea when that will be, but I'll try to keep you guys posted. Yeah, I can imagine it's not always easy to follow, especially since some things I might take for granted, and I have no idea or various people are familiar with, the iCE40 architecture, like the blocks, what's a cache, and all that kind of stuff. And yeah, explaining is not always not easy. Yeah, I mean, just it's important to understand how so something I didn't show here because that's something I did several weeks ago, but I actually looked at the behavior of the PyCoRV and of the VEX RISC-V, how much like the access patterns that they were doing, to have a kind of an idea of. Actually, do I? Give me a second. I might have a trace. Yeah, I do have a trace somewhere. Um, so that's a trace from a Vex RISC-V executing some code, right? And this is with an instruction cache. And so what you can see is here, like these bursts. So that's or everything that starts with I underscore is the instruction wishbone bus. And everything with D is the data wishbone bus. And here you can see these bursts of like 1, 2, 3, 4, 5, 6, 7, of 8 words. So 8 words of 4 bytes, 16. So that's it obviously has a cache line size of 32 bytes. And you can see it's basically preloading the instruction cache here. All of this, and then it actually starts executing code, and you see that here it's executed. So this is just a printf, like it just outputs stuff to a UART peripheral. But like from that point on, when it starts executing printf, you can see that it executes everything from its internal cache, because it's a very small code size. But it does still access the data bus, so you still have accessing to the data space here, that kind of stuff, and that's kind of I took traces like that for the Vex, for the Pico V32, for the Vex with a cache and without cache, to see what kind of access patterns it did, so that when designing the cache and doing through the design process that I just did now, I had some idea of what kind of access the CPU would do, and when making choices, I could try to make some, decent choices that are actually gonna work out. So yeah, that's basically all. Or you design something is first gather as much information as you can, and then I don't know if I have make sock Pico Heavy 2. I'm just checking something on my laptop if I have a trace, if I have the equivalent trace for the Pico RV. 32. Where is that trace? Yes, okay. Because something else I actually did as well is, I mentioned that my target frequency was 30 megahertz. Obviously, I didn't pick that randomly. It's 30 megahertz mainly to provide some margin above 24, because in the Secret Python case, it has to run on the BitC, which includes a USB core, which means the USB core needs to run at 48 megahertz. But there's no way the Pico RV, there's no way yet the Pico RV or the Vex is gonna hit 48 megahertz. Like that's not gonna happen, which means I need to run it at 24 or 12 megahertz. Just because I only have one PLL, I can only divide the clock and that kind of stuff. I can't generate just tons of arbitrary frequency. And so the Pico RV32 is slower than a VEX in the sense that it takes more cycles to execute, but I can't hit 24 megahertz with the VEX, which means it's actually faster to use the Pico RV32 running at 24 than the VEX running at 12. I can actually retire more instruction per second. So that's the kind of stuff that I had to look up beforehand. But if we look at the access pattern for the Pico RV32, let me load. So the Pico RV32 only has one wishbone bus, so it doesn't have multiple. But you can see that there is no cache, which means that you see that the mem valid, that's the signal that indicates that we actually have request on the bus. That's high a lot, because basically for every single instruction we need to fetch a new word, so it takes a lot more time, and the bus is a whole lot more busy than the VEX, where and so you can see, like for instance here, like executing the entire program took 7 microseconds. In the case of the VEX, it took 4.6 microseconds. So the VEX was much faster, but if I have to run it at half the frequency, well, that would have taken 9 microseconds, which means the Pico RV32 turned out to be faster. So yeah, let me just read the chat in case there was. Oh yeah, oh yeah, right. Zooming in the. Huh. I have no idea to do that. Yeah, I don't think you can, right? Oh wait, you can. Oh no, that's just yeah. Right. Yes, you're right. The clock to instruction ratio of the Pico RV is worse, but it has a higher Fmax. That's the thing, is that a Pico RV32, I actually have a Pico RV32 that runs at 30 megahertz on the icebreaker. A VEX, I can maybe hit 20. And so if I restrict myself to multiple of 12 megahertz for USB, my choices are 12 or 24. If it doesn't hit 24, I'm stuck with 12. And the VEX is not twice as fast as the Pico RV. So that's the problem. It like the clock per instruction ratio is obviously like a important metric, but it's not the only one. You have to consider a lot of other things. Yeah. Yeah, it's not. I mean, we can. I don't actually know if we. It's. Problem is here we don't see. Yeah, I don't have the proper graph to show the difference here, but yeah, that's the gist of it basically. But yeah, like benchmarking different implementation of RISC-V is something I've been trying to do recently, to exactly trying to find the best option for various use cases. Because like if I want to boot Linux, as I mentioned in the beginning, well, I don't have a choice. Like I pretty much need to use the VEX. Now the PyCurve definitely doesn't need 6 cycles per instruction. It needs 3 or 4, depending on how fast you can feed him instruction, basically. Because I always have 1 delay of latency to feed him instruction just to meet the timings, it often needs 4 cycles. And you can actually see it in the, for the PyCurve, you can actually see it pretty easily here. If you look, so like that's 1 instruction. Like this interval is 1 instruction, because it's the delay between 2 instruction fetch, and you can see that this is 1, 2, 3, 4 cycles, and oh well, actually looking at this sorry, this should have, that should as you can see here, the bus access is actually longer. That's actually a trace of a simulation where I artificially added the latency of the cache to see the impact of an additional well, the problem, I can open the VEX, that's the VEX thing, but the problem is because the VEX as an internal instruction cache, I actually don't know. I don't have any external sign of when it has retired instructions. That's the problem. Like that's the trace from the VEX. I can look at it, but the problem is I don't have any signal that tells me when it has executed an instruction, basically. So one thing I can do is just compare the kind of the number of cycles between 2 write to the UART. So that I can do. Let me just remove the artificial delay that I put on the PyCurve v32. Okay, so we can see here that we have a bunch of access to the UART, right? So I'm just gonna look at how much time there is between 2 of them. So I wish that GTK Wave had a better system for this. So there is 209, basically 290 nanoseconds for the PyCurve v32. And if I look at the VEX, so if I get the access to the here, I have (130 nanoseconds). So yeah, actually in this case, like because the because this particular loop fits entirely in the instruction cache inside the VEX, here the VEX is actually twice as fast as the PyCurve, slightly more. But of course that doesn't account for all this, which all that time that it took actually loading the cache. I unfortunately don't have I don't have a VEX core built at the moment without the instruction cache. Yeah, exactly. The PyCurve is much more likely. Like the PyCurve doesn't have twice the Fmax of the VEX. Like right, it's maybe 1.5 times faster, something like that. It's just that if I limit myself to frequency I need to run USB, I only have the choice between 12 and 24. That's the problem, because I could probably run the VEX at 20 megahertz, but I could also run the PyCurve at 30. But that doesn't help me. Like to run USB I need 48, 24, 12. So yeah. If you rely on the PLL capabilities and other requirements of design. Yeah, exactly. If you limit yourself to what you can actually do with the PLL, which is very limited, you're gonna run the PyCurve twice as fast, basically. And that's like in the FOMU, he runs the VEX at 12 megahertz because there is no way to run it at 24. Yeah. Okay, so I think I'm gonna end here because it's actually getting late. So thank you everyone for joining, and I guess see you next time. I have no idea when that will be. Actually, you can also tell me if that's a convenient time for you, or oh, hey Greg, you're arriving just in time when I finish. Yeah, well, thank you guys for joining, and I will need, and yeah, tell me if you have any feedback, or because I mean that's definitely the first time I stream, so I tried to have a basic setup working, but as you can see, there is definitely something that are not working. I'm not sure why my icons are black on the capture. They're definitely not on my screen. Wait, does that? No, I have no idea what that is. Okay, I mean my setup a little weird, but yeah. Anyway, or if you would prefer streaming at another time or whatever, you can always message me on Discord. Okay, bye.